All right, this video will provide you with the foundation for the parent function benchmark. There are several functions that we believe you need to have memorized, what they look like. You need to be able to do transformations. This will help with domain and range. This will help later when we get to integrating and doing sign charts and lots of things. So these functions are what we think are crucial to being successful later on the AP Calc exam and just in general for calculus. Probably not for your general life, but definitely in calc. So first functions that you have to have memorized. You should know what these graphs look like. You should be able to draw these graphs yourself. Y equals x squared. Hopefully everybody knows. There's our smiley face. It goes through 0, 0, ideally, right there. Domain is all reals, which we are going to denote negative infinity to infinity. Range in this case is 0 to infinity, only positive numbers, and we want to include, and this is going to be sort of an important thing, especially on this benchmark, knowing whether 0 is included or not included. To include, we are going to be a little more picky. Instead of a little sloppy parentheses, we are going to build a house with straight rectangular walls for our 0 to make it feel welcome. So that means 0 is an output. So your domain here is negative infinity to infinity. X cubed is the little snake, also going through 0, 0. This is also a power function. These guys actually continue forever, so I'll put little arrows. Its domain is also negative infinity to infinity, and its range is similarly negative infinity to infinity. Now, later on, we're going to do transformations to these functions, and it's important to remember that anytime your domain or range is negative infinity to infinity, I don't care what basic transformation you do, shifting, stretching, flipping, you aren't going to change a domain and range of negative infinity to infinity. If you can put in any number you want, shifting it still will give you a domain of any range, any number you want. Next, we're going to look at absolute value of x. That is our nice V shape, also going through 0, 0. It too has a domain of negative infinity to infinity, and it has a range of 0 to infinity, again including 0. So we're going to make that hard bracket to say that we are including 0. One thing to note about this will be important when you are doing transformations of stretching vertically, is that the slope of this line is 1, or actually negative 1 when you're coming down the back side, but up 1 over 1 or up 1 back 1 are your slopes. And that will change when we do vertical stretches. That will be important later on. Our next parent functions are square root of x, which Ms. Rainey likes to call swimmer's arm. Right? It goes up. It increases forever. This does not level off. It never levels off. It just increases less and less quickly. The domain here is 0 to infinity. Including 0, you can take the square root of 0. You get 0 out. However, you cannot take the square root of a negative number. So this point right here is our boundary. Now when we shift, that is going to be our critical point. So this is an important point to follow. Similarly, when we get to this right here, this point is going to be an important point to follow. This point will be an important point to follow. This point will be an important point to follow. So those are critical numbers. When we do our transformations, I want to know where that point ends up. Our range is actually, in this case, the same as our domain. We can get a square root that equals 0 when we take the square root of 0. So we include 0, and it can go all the way up to infinity. That is another way of saying this. It does not level off. It keeps going up. Our next two functions are our inverse power models, 1 over x, 1 over x squared. And be careful with your drawing. If you do these on your calculator, you are going to get this thing at the bottom, or this thing at the bottom right here, these guys. And it looks like they just sort of come down and end, like that's it. And that is not true. These both have double asymptotes. That's true of your inverse power models. They have double asymptotes. So there's one asymptote when y equals 0, and another asymptote when x equals 0. Because you cannot put 0 in for x. That is a restriction on your domain. You can put any other number you want in, so negative infinity to 0, and in this case we are not including 0. So I don't need to build a nice solid little house. I just use a parentheses, 0 to infinity. And what 1 over x looks like is my boomerangs, right? And we are showing asymptotic behavior. We get closer and closer to our asymptotes, but we do not touch them. That's this graph right here, right? The important key features for these when we're doing transformations are the asymptotes. Where do they end up? The range on this is the same. It's negative infinity to 0, not including 0. This is our union symbol, which means both of these are included. 1 over x squared is what I like to call the volcano. And that also has a domain restriction of 0. You cannot divide by 0 again. Same here. When x is 0, you end up dividing by 0. So we can't do that. And our range, oops, negative infinity to 0 is just that. We do, oh no, it's not negative infinity to 0. Sorry. It is 0 to infinity. Only positive numbers come out of 1 over x squared. All right. Our next pair, e to the x and ln of x. Very, very important in calculus. E to the x is exponential. It's similar to 2 to the x, 10 to the x in shape. It has a horizontal asymptote of y equal to 0. It includes the point. When x is 0, we are doing e to the 0, and we get 1. It includes the point 0, 1, and that is going to be a crucial point I want you to follow. And then it grows exponentially, and when we have negative exponents, that flips our fraction, and we end up dividing by bigger and bigger numbers, and so we get smaller and smaller. Our domain is all reals, and our range is 0 to infinity, but because of the asymptote, again, we do not include 0. Be careful with your drawing. It does not just come down and hit the axis. No, no, no. This is asymptotic behavior. So the things you will have to follow when you do your transformations are the point 0, 1 and this horizontal asymptote. Now, ln of x is the inverse of e to the x. So if e to the x has the point 0, 1, ln of x has the point 1, 0. You flip your x and y. And ln of 1, e to what power, right? There's a hidden base of e. E to what power would give me 1? Well, e to the 0 would give me 1. That's why it has the point 1, 0. E to the x has a horizontal asymptote at y equals 0. So ln of x has a vertical asymptote at x equals 0. Again, switch your x and y. Instead of y equals 0, we get x equals 0. And our ln of x graph looks like this. The other thing about inverses, domain and range switch. So the domain is, you can't take the ln of 0, so we do not include 0, but you can take anything coming back to 0, and then your domain goes all the way up to infinity. And our range is negative infinity to infinity. And remember, if you're looking at your calculator, it's going to sort of trick you, and a lot of people think, oh, it just ends right there. No, 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 no. It is asymptotic, and it keeps going down closer and closer to that asymptote. All right, two more. Sine of x and cosine of x. You have to understand the graphs of sine of x. One cycle for sine. Sine starts on the sinusoidal axis and goes up. And we can trace one backwards. I will want to see both an x and a y scale. So sine goes as high as 1, as low as -1. And this is going to be pi. One cycle, one period, is 2 pi, which would make this negative pi, negative 2 pi. So my domain for sine, again, is negative infinity to infinity. This pattern continues forever. The range is from -1 to 1, including -1 and 1, because you can have a sine that equals -1 or 1. Cosine starts at the very top, and it comes down. That is one cycle of cosine. Once again, that's 2 pi. That puts pi as the x-coordinate for our minimum value. And coming backwards, this would be -2 pi. And this would be pi. And once again, it goes to 1 and -1. X and y scales will be important on this parent function benchmark. Its domain and range are the same as for sine. All right, so those are our parent functions. Other things you're going to need to know for this benchmark, you need to understand even and odd, which of these are even and odd. Even functions, you can have lots of options here, but basically your thing, so you should have -4 to 4 for your domain and 0 to 3 for my range. So I'm not going to be down here. Range of 0 to 3 means I want something up here. So if whatever I do here, I have to repeat that way. That's my even function. You could have other options, but you should not have anything down here because of this, 0 to 3 for my even function in this case. Domain here, so an odd function, if I start with the same deal right there, and remember odd functions need to go through 0, 0, and then so then I would go, the negative ones would give me the opposite, and this would have to be -2, and that would be as high as 2. Now there's other options, but that's one. Then the last thing we're going to do right here is go back for each parent function, label if it is even, odd, or neither. So even, remember, for even functions, we're saying f of the opposite of x gives the same y value of f of x. That's our symmetry, right? If I go to -3 or to 3, I get the same y value out. If I go to 1 or -1, I get the same y value out. Whereas odd is f of the opposite of x is the opposite of f of x. So when 1 gets me a y value of 2, then -1 would get me a y value of 2's opposite, which is -2. So let's go back and see which ones are even, odd, or neither. And it's fairly obvious. X squared, this has our reflectional symmetry. This one is even. X cubed is odd, and in that even odd video, as we talked about, the power on x is odd, the power on x is even. Absolute value of x has that reflectional symmetry over the y-axis. That's an even function, and that's sort of what absolute value means. If you put in x or the opposite of x, you get the same answer out. Let's get rid of these. Square root of x, the swimmer's arm, is a neither. There is no reflectional or rotational symmetry. 1 over x, this function, if you reflect over the y-axis, you do not get the same, but if you rotate 180 degrees, you do get the same. This is odd, and 1 over x squared is another even function. Here we go. E to the x, this one is a neither. There is no reflectional or rotational symmetry, and same for ln of x. And then finally, when we get to sine and cosine, sine does not have that reflecting. If I take this and I try and flip it backwards, actually that won't get me the same thing, right? If I come back here, it would look like that, and that is not even. This one is indeed odd. If I imagine, let's get rid of this. Let's actually do this right here. I don't know how good this will be, but we'll give it a try. If I take this and I rotate it 180 degrees, if it was a nice little thing, I would get essentially the same graph. So this one's odd. And then finally, cosine of x does have that reflectional symmetry, and this one's even. So those are the parent functions you need to have memorized. You should be able to draw those graphs from your memory. And then later we're going to talk about transformations to these graphs.